Okay, we're happy to have Zach Mckenzie speaking on well-founded models of fragments of collection. Longer title, so but go ahead, Zach.
Cool. Thank you so much, Atta. Thank you so much. It's great to be here. I suppose good afternoon for you guys, right? Um, cool. So what I wanted to do today actually is so I'm going to compare two different versions of the set theoretic collection scheme over a set theory that contains the power set axiom. So throughout the talk, L will be used to denote the language of set theory. So as usual, this is uh, just first order logic with a binary relation whose intended interpretation is membership, and that I'll pronounce in. If L prime is an expansion of the language of set theory, then I'll use delta naught L prime, sigma 1 L prime, etc., for the analogues of the Levy classes of L prime formulae. As usual, if L prime is equal to L, then I'll denote these classes just delta naught, sigma 1, pi 1, etc. If T is some theory and gamma is a class of formulae, then I'll write gamma superscript T for the class of formulae that T proves are equivalent to a formula in gamma. So today I'll be speaking about some sometimes weak subsystems of Zermelo-Fraenkel set theory. So TCO is an axiom that I'll sometimes include in these theories that states that every set is contained in a transitive set. So I just wanted to go on to describe some of the schemes that I'll use to build axiomatized subsystems of Zermelo-Fraenkel set theory. So let L prime be an expansion of the language of set theory, and let gamma be a collection of L prime formulae. So gamma separation is the scheme that asserts that for every formula phi of x in gamma, and for every set x, we're guaranteed the existence of a set Y whose elements are exactly the things in W that satisfy phi. And note we're allowing parameters in phi. So the gamma collection scheme is the scheme that asserts that for every formula phi x y in gamma, and for every set W, if it's the case that for every x in W, there exists a y such that phi xy holds, then we can find a collecting set C such that for every x in W, there exists a y in C such that phi xy holds. So there's an alternative version of the collection scheme that I'll call strong collection. So strong gamma collection is the scheme that asserts that for all formulae phi xy in gamma, and for all sets W, there exists a collecting set such that for all x in W, if there exists a y such that phi xy holds, then we can find such a y in the collecting set C. So note that on the face of things, I mean, strong collection does look stronger than the collection scheme because we're relaxing the requirement that that the phi satisfy the antecedent of the collection scheme. However, if we start with some base theory like MacLane set theory, then adding collection for all L formulae obviously yields ZFC, and we also get ZFC if we add strong collection for all L formulae. However, we'll see that if we restrict our attention to formulae that are in the Levy pi n classes, then strong collection is indeed stronger than collection. Cool. So another scheme that I'll need to define subsystems of
Sorry,
Zermelo.
can you say that again? I think I missed that. You're saying that a priori, we might think strong collection in some cases is equivalent to regular collection, but I think
Oh,
I missed. Wait, did you say that there was some cases where it's not equivalent, or?
sorry, yeah. Okay, so I mean, we could add, if we add collection for all L formulae to something like McLean set theory,
Hmm.
then we get ZFC, right?
Hmm.
And you also get ZFC if you add
Hmm.
strong collection for all L formulae. So it doesn't, if you just strong collection for all L formulae, doesn't give you anything stronger than ZFC.
Hmm.
So we'll see that collection for pi n formulae, however, is weaker than strong
I see.
collection pi
Okay,
n form. Yeah,
thank you.
sorry, no worries. It's cool. Uh, so class foundation. So gamma foundation is the scheme that asserts that for every formula phi x in gamma, if phi defines a non-empty class, um, then we can find an in minimal element of that class. So if gamma is just the single formula x is in Z, then the resulting single axiom just says that every set has an in minimal element. And this is usually referred to as regularity. And today I'll call it set foundation, just to be. If gamma is the collection of all L formulae, then the resulting scheme is referred to as class foundation. Cool. So finally, I just wanted to mention the delta n separation scheme. So this this asserts that we have separation for every formula that's delta n. So if phi x is a formula that's sigma n, and phi is equivalent to a pi n formula, then we have separation for phi. Okay, so this brings me to introduce the set theories that I'm going to use as the base theories for my discussion today. So when I'm speaking about subsystems of Zermelo-Fraenkel set theory that don't contain the power set axiom, my base theory is going to be Kripke-Platek set theory with infinity. So this is the set theory axiomatized by extensionality, pair, empty set, union, infinity, bounded separation, bounded collection, and pi1 class foundation. So it's worth commenting that earlier presentations of Kripke-Platek set theory included full class foundation in its axiomatization, but it's now become kind of more standard to axiomatize it with pi1 class foundation. And some people prefer to talk about set induction rather than class foundation. And roughly speaking, gamma class foundation is equivalent, over a strong enough base theory, gamma class foundation is equivalent to set induction for the negation of all formulae in gamma. So you may also see Kripke-Platek axiomatized with sigma 1 set induction. Cool. The set theory that I'm going to use as the basis for my discussions of subsystems of Zermelo-Fraenkel set theory that contain the power set axiom is the set theory M. So this is McLean set theory minus the axiom of choice. It's axiomatized by extensionality, pair, empty set, union, power set, bounded separation, TCO, and set foundation. Cool. So what I want to do is I want to compare today M plus pi n collection with M plus strong pi n collection. So compare fragments of collection with fragments of strong collection over M. Now I'm only ever going to refer to pi n collection and strong pi n collection. And this is because over M, pi n collection is equivalent to sigma n plus 1 collection, and strong pi n collection is equivalent to strong sigma n plus 1 collection. So another important consequence of the collection scheme is that it allows us to show that the Levy sigma n classes and pi n classes are essentially closed under bounded quantification. So in particular, if T is a set theory that contains M plus pi n collection, then the classes sigma n plus 1t and pi n plus 1t are both closed under bounded quantification. So some of the set theories that I'll refer to today are too weak to build the cumulative hierarchy. So I just wanted to give you an indication of where at what point we're able to to build the cumulative hierarchy. So the theory M plus pi 1 collection plus pi 2 foundation is capable of proving that the function that maps alpha to V alpha is total. But the theory M plus pi 1 collection does not. So the intuition is that the difference between M plus pi n collection and M plus strong pi n collection amounts to how much separation is available. So M plus pi n collection is capable of proving delta n plus 1 separation. And over the set theory M, strong pi n collection is equivalent to pi n collection plus sigma n plus 1 separation. So note that nothing I've told you so far, however, tells us that there's any difference between M plus pi n collection and M plus strong pi n collection. So that's what I want to convince you of on this slide. So throughout this talk, I'm going to be referring to models of set theory. Some of these models will be non-standard, so I want a way of distinguishing between points in the model and their extension. So as long as let M be a structure in the language of set theory and A be a point in that structure. As long as M is clear from the context, I'll write A star for the collection of X in M that M such that M believes that X is in A. So for the extension of A. So the next result shows that essentially shows that M plus strong pi n collection is equiconsistent with M plus pi n plus 1 collection. So if M is a recursively saturated model of M plus strong pi n collection, and if n is greater than 0, then we can find a cut of the ordinals of M such that if we take the union of the V's along that cut, then the resulting structure satisfies M plus pi n plus 1 collection. So obviously if n is equal to 0, then M plus strong pi zero collection doesn't necessarily have access to the V hierarchy. However, we can get around this with a little bit of choice. So if M is a sorry, too many M's. If M is a recursively saturated model of M plus strong pi zero collection, then there exists a transitive subclass N of M such that N satisfies M plus the axiom of choice plus pi 1 collection.
Zach, so since I said that I would have to leave soon, I want to ask one question now. That so by cut you read something that's just closed under the successor, or also on
Oh,
limits?
yeah, I'm really yeah, sorry about that. Yeah, I was thanks. Yeah, so a cut by cut here I mean just something that's closed under successor. But I also want it to be the case that there's no that it's not realized as a set, so that there's no least
Oh, so it's
order.
like a proper cut. So in the sense.
Yeah, yeah.
I
Sorry.
see. But are there any interesting combinatorial properties of that cut, or just existence that comes from the proof?
Uh, I mean, so yeah, I mean, just existence. So I mean, it's
Hmm.
just kind of um try to build a model. Try to build a model that's like a level of the V hierarchy that's elementary enough to satisfy M plus pi n plus 1 collection. And you don't necessarily succeed, but you can overspill to get a cut that's
Hmm.
that's
So,
that
so,
that
so,
is
so you get it by overspilling something. I see.
yeah.
All right. Thank you.
Um, cool. So we can also see that M plus strong pi n plus 1 collection is able to prove the consistency of M plus strong pi n collection. So I mean, if you start trying to build a level of the V hierarchy that's elementary enough to satisfy M plus strong pi n collection, then you're able to succeed if you have you can see that you're able to succeed if you have M plus strong pi n plus 1 collection available to you. Um, so this shows that M plus strong pi n plus 1 collection proves the consistency of M plus strong pi n collection. So putting these two results together, we see that M plus strong pi n collection is able to prove the consistency of M plus pi n collection. Right? So M when n is greater than 0. So M plus strong pi n collection proves that there's a transitive model of M plus strong pi n minus 1 collection. And then you can turn that model into a model of M plus pi n collection. Cool. So this shows that M plus strong pi n collection is indeed stronger than M plus pi n collection, and a stronger consistency strength. So there's no analog of this result when n is equal to 0. So Adrian Mathias, in his paper on the strength of McLean set theory, shows that M and M plus strong pi 0 collection are equiconsistent. Okay, so we know that M plus strong pi n collection proves the consistency of M plus pi n collection, but the argument kind of goes via these non-standard models. So this raises the question: does M plus strong pi n collection prove that there exists a transitive model of M plus pi n collection? And so this is the question that I want to address today and answer negatively. So in fact, I'm going to show that every transitive model of M plus pi n collection satisfies strong pi n collection. Okay, so the proof is going to go via an end extension result for subsystems or for transitive models of set theory. So I just wanted to remind you that in the context of set theory, we have two different notions of end extension. So let M and N be structures in the language of set theory, such that M is a substructure of N. So we say that N is an end extension of M, and write that like this. If in the process of going from M to N, no new elements of any point in M is added in N. And then we also have the notion of power set preserving end extension, which is written like this. So we say that N is a power set preserving end extension of M if in the process of going from M to N, no new subsets of any point in M are added in N. So, for example, most forcing extensions of models of set theory will be end extensions that are not power set preserving. And the intuition is that a power set preserving end extension is really going to add things onto the top of your model. So I'm also going to want to talk about end extensions that are elementary. So we say that N is a sigma n elementary end extension of M, and write that like this. If N is an end extension of M, and every sigma n property of things in M are the same in between M and N. Cool. So what I want to do is I want to build end extensions using the bar-wise compactness theorem. So let L prime be an expansion of the language L, and fix some sufficiently simple coding of the infinitary language L prime infinity omega. So this is the language that contains all the non-logical symbols of L prime, but allows arbitrarily long conjunctions and disjunctions, but only finite blocks of quantifiers. So then, given a transitive model of Kripke-Platek set theory with infinity, we can consider the fragments of L prime infinity omega, whose codes lie in this transitive model M. And I'm going to use L prime M to denote this fragment. Okay, so this is the version of the bar-wise compactness theorem that I want to use to produce end extensions. So suppose that I've got two expansions of the language of set theory, L prime and L star, and suppose that that M is an L star structure that's countable and transitive, and satisfies all the axioms of Kripke-Platek set theory with infinity, plus bounded separation for every L star formula, and bounded collection for every L star formula. So this is the analog of Kripke-Platek set theory with infinity, but in the expanded language L star. So now suppose that we have an infinitary theory T formulated in L prime M, so the infinitary language coded in M. And suppose that this theory is sigma 1 L star definable over M. If it's the case that every subset of this theory that's coded in our model M is consistent, then T itself is consistent. So with the bar-wise compactness theorem, so we can prove this end extension result. So let M be a countable transitive model of M plus pi n collection, then there exists n, a proper sigma n elementary end extension n of M, such that n satisfies M plus pi n collection plus full class foundation, and there exists a point D in M that contains every point from M. So note that that M here is transitive, so it automatically satisfies full class foundation. So I'm not requiring that N satisfy any more theory than I know holds in M. So I'll try and be quick with this proof sketch. So let L star be an expansion of L that's obtained by adding a new binary relation symbol S. So then just interpret this new binary relation S as a sigma n satisfaction class over M. So then so note that a sigma n satisfaction class over M is going to be sigma n definable over M. So then extend the model M with S, and note that since the original model M satisfied pi n collection, the extended model, once we add this this satisfaction class, is going to satisfy delta naught L star separation and delta naught L star collection, where we can now refer to this satisfaction class. So now we can use this extended model M star in a barwise compactness argument. So let L star extend the language of set theory by adding new constant symbols A bar for each A and M, and a new constant symbol boldface C. So now just what I want to do is I just want to express an infinitary language T expressed in the language L prime M, so the infinitary language coded in M, that says that a model of T is going to be a sigma n, a proper sigma n elementary end extension of M. That satisfies M plus pi n collection plus full foundation. So let T be contain M plus pi n collection plus full foundation. So then also put the following scheme in T. So this scheme is just saying that essentially that the embedding of M we get into a model of T from these constant symbols is going to be such that that M is realized as a transitive submodel of the model of T. So the models of T are going to be an end extension of M. So then add a scheme which says that that C, this boldface C, contains every point A from M. And finally add the scheme. So this final scheme is just going to say that the model of T is going to be a sigma n elementary extension of M. And so note that that since we have this satisfaction class available to us in M star, this theory T is sigma 1 L star definable over M star. So we can apply the barwise compactness argument. So note that any subset of T that's actually a set in M only contains set many of the constant symbols A. So we can interpret these constant symbols in M itself, add an interpretation for the constant symbol C, and see that that theory, that subset of our theory T0 is consistent. So by the bar-wise compactness theorem, this theory is consistent, and a model of this theory just yields a sigma n elementary end extension of M. Cool. So this so I'm now at the point almost at the point where I can prove that every transitive model of M plus pi n collection satisfies strong pi n collection. So I just need two straightforward lemmas before I give that argument. So the first, so suppose that I've got two models M and N of the set theory M, such that that N is a sigma 1 elementary end extension of M. Then the sigma 1 elementarity guarantees that N is going to be a power set preserving end extension of M. So this just follows immediately from the fact that M satisfies the power set axiom, and then the formula, the equation that says y is equal to the power set of x is pi 1. So power sets from M are going to be the same in N, and this means that N has not added any new subsets of any point in M. Cool. So I mean, so this next result you'll recognize as just a an elementary result from set theory. So it says that every strict well-founded partial order R on a set X has a rank function H from X to an ordinal, such that for any X and Y in X, if X is related to Y by R, then H of X is strictly less than H of Y. So I just wanted to note here that the existence of rank functions for strict well-founded partial orders can be proved in Kripke-Peitic set theory with infinity plus sigma 1 separation. Okay, so I can now prove the main result. So I'm going to show that if n is greater than 0, and M is a countable transitive model of M plus pi n collection, then M actually satisfies strong pi n collection. So as I mentioned at the beginning, over the set theory M, in fact over a much weaker base theory, strong pi n collection is equivalent to pi n collection plus sigma n plus 1 separation. So we just need to show that that our countable transitive model M satisfies sigma n plus 1 separation. So let theta xy be a pi n formula. Let B be a set, and A be parameters for theta. And suppose that I want to prove the instance of sigma n plus 1 separation. For the formula, there exists a y, theta xy. So I want to show that the collection of points in B, x, such that there exists a y theta xy holds, is a set in M. Okay, so using the end extension result that I spoke about on the preceding slides, let n be a proper sigma n elementary end extension of M that satisfies M plus pi n collection plus full class foundation, and such that there's an ordinal alpha in N, a new ordinal in N, such that every point in M is contained in V alpha in N. So this is easily arranged from from the end extension result that I mentioned on the preceding slides. So now work inside this end extension n and consider the collection of all x in B such that there exists a y in V alpha such that theta xy holds. So note that so I'm now inside n. I'm bounding this existential quantifier here by a set. So I can use pi n separation to show that the D is actually realized as a set in N. So note, however, that D is just a subset of B, and N is greater than 0. So we know that small n is greater than 0. So we know that the end extension N is a power set preserving end extension of M. So since D is just a subset of B, this means that D is really a set in M. So note that there's no reason to think that D is the set that we want to show exists, but since every point in M is in V alpha in N, D is a superset of the collection that we want to show exists. Okay, so work inside N again. And inside N, we can use delta N plus 1 separation to define a function G that ranks the elements of D according to the rank of the least rank of a witness that puts that thing inside D. So in other words, for every x in D, define G of x to be the least rank of a y in V alpha, such that theta xy holds. So this ranking function induces a well-founded strict partial order on D, defined by for all x0, x1 in D, x0 is less than x1 if and only if G of x0 is strictly less than G of x1. And note that this well-founded strict partial order has the property that it puts things with witnesses in M lower down, strictly lower down than things that don't have witnesses in M. So now note that this well-founded strict partial order triangle is just a subset of D cross D. So again, we can use the fact that the end extension is a power set preserving end extension of M to see that this well-founded strict partial order is actually realized as a set in M. And note that the elementarity between M and N guarantees that this strict partial order remains well-founded in M. So now work inside M, and note that M, M's going to satisfy all the axioms of Kripke-Platek set theory with infinity, plus sigma 1 separation. So inside M, we can find an ordinal gamma and a function from D to gamma such that H is a rank function for this well-founded strict partial order. So using this rank function, we can then define slices of this set D. So for every xi in gamma, define D of xi to be the set of all x in D, such that h of x is less than xi. And note that there's no problem showing that for every ordinal xi in gamma, d xi is a set in M. So now we can just use the fact that our model M is genuinely well-founded, to see that, well, either this set D is the set that I was looking for, or we can use the fact that M is genuinely well-founded to see that there must exist a xi and gamma such that that D xi is the set that I want to show exists. And so this shows that sigma n plus 1 separation holds in M. Okay, so it's worth reflecting on the assumptions that I made when proving that result. So the first, I suppose, natural question to ask is there an analog of this result when n is equal to 0? So the following example shows that the answer to that is no. So let M be an omega model of Zermelo-Fraenkel set theory with choice, with a non-standard ordinal that's countable according to M. So then consider the well-founded part of this this non-standard model, and so using a result that's due to Harvey-Friedman, this well-founded part is going to be a model of a set theory called KPP, and it's going to inherit the axiom of choice from M. And note that this set theory KPP contains the power set axiom, and satisfies a fragment of collection that's actually stronger than delta naught collection. And note that every ordinal in this model of KPP that we've produced is countable. So that means that there's going to be a well ordering of, for example, the power set of omega in this model that's too long to be isomorphic to any ordinal. So this means that this model can't satisfy sigma 1 separation. So the other interesting thing is that this result of Richard Gostanian shows that the power set axiom was actually necessary in this proof. So Richard Gostanian was studying minimum models of subsystems of Zermelo-Fraenkel set theory, and it follows from his results that if alpha is the least ordinal, such that L alpha satisfies Kripke-Platek set theory with infinity plus pi n collection, then this L alpha does not satisfy sigma n plus 1 separation. So power set was necessary. Okay, so so the next obvious thing to ask is whether this assumption that the model that satisfies pi n collection is well founded, whether this second order assumption of being genuinely well founded can be replaced with a first order assumption. So, for example, that M satisfies some fragment of class foundation. So it turns out that the answer is yes. So there's obviously kind of two parts that we need to check. So the second part of the proof that I went through, you can see that that I only used foundation in that part of the proof at the very end, at the very last step, and it was clear that that at that last step I was appealing to pi n plus 1 foundation. So what looks a little bit more difficult is the end extension result, because Barwise the Bauweiss compactness theorem really only applies to well-founded models. So it turns out that one can get around this using admissible covers. So this is a kind of machinery developed by Bauweiss and presented in the appendix of his book, actually. So using admissible covers, one can get the following end extension result that can be used in place of the end extension result for transitive models that I sketched the proof of. So if T is a recursively enumerable L theory that contains M plus pi n collection plus sigma n plus 1 foundation, and M is a countable model of T, then there exists a proper sigma n elementary end extension n of M such that n satisfies T, and there exists a point D in n that contains every point from M. So note that it looks like there's a mismatch between the amount of foundation we've used here. So the second part of the proof looked like it was using pi n plus 1 foundation. And to get this end extension result, it looks like I'm using sigma n plus 1 foundation. So a result due to Reser kind of allows us to reconcile this mismatch. So M plus pi n collection plus pi n plus 1 foundation proves sigma n plus 1 foundation. So putting those kind of three pieces together, we're able to prove this relationship between subsystems of ZF that contain the power set axiom. So M plus pi n collection plus pi n plus 1 foundation actually proves sigma n plus 1 separation.
I'm sorry to interrupt. Do you need M in the result by Reser?
Sorry?
Or can you do the result by Reser in KPI?
Yes, with V equals L. With V equals L, I think.
I guess, yeah.
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 With V equals L, I think, yeah.
But without V equals L, no.
Yeah, I don't think, or you need some kind of, so you're using, you're definitely using some kind of stratification of the universe, right? So some kind of way of putting your universe into levels. So I mean, V equals L would work, but it would also work if V was equal to L of something, for example, as long as, I mean, the issue is models of KPI can look really bizarre, I think. But it would be an interesting, I think it's an interesting question to ask if this goes through in KPI alone, or if there are examples of strange models of KPI where I think that's not known. But, that's I think that's all I want to say. Just finally, so there's no hope of weakening this assumption of pi n plus 1 foundation to sigma n plus 1 foundation, because another result due to Reser shows that sigma n plus 1 foundation over n plus pi n collection doesn't prove pi n plus 1 foundation. And sigma n plus 1 separation is going to prove both pi n plus 1 foundation and sigma n plus 1 foundation. So there's no hope that sigma n plus 1 foundation proves sigma n plus 1 separation. Cool. Thank you so much. Thanks.
Great. Let's thank Zach. And we can take questions.
Yes, okay. You have these two base theories, the formal base theory M, and yet when you want to call on the Barwise compactness, you switch to KPI, right, which has what you need to carry that out. So, could you remind me what the relation is between these theories? KPI seems much stronger, right? And exactly where is this jump going to the stronger theory?
KPI is much weaker, right? So with no power set. So KPI looks like a a subsystem of, or could be as weak as a subsystem of second order arithmetic. While
But can you remind me, does M have infinity, McLean?
yeah, yes. So here's M. Is that you can still see my screen, right? Yep.
Yep.
And so even when you have infinity, you still need transitive containment as a separate axiom?
Yeah. I mean, so Zermelo set theory doesn't prove transitive containment.
Okay.
So yeah. I mean, so Zermelo set theory uh, isn't capable of proving class foundation, even though it has full separation available to it.
Okay, so anyway, when you switched to using KPI, that was safe because it's a much weaker theory, is that right?
Yeah, so what did I yeah, and I have a as soon as I'm adding, I mean, as soon as I'm adding collection to M. So I mean, so what M doesn't have is M doesn't have any collection at all.
Oh,
Um,
okay.
but but I mean, all by I'm as soon as I'm doing anything, I'm adding collection to M. So I end up with something that contains KPI. Is that so? I mean, so here, I mean, even with so I probably should have said probably N needs to be greater than 0 here. But as soon as I have N, yeah. So sorry. So thank you. That's a mistake. A mistake in the slides. As soon as N is greater than 0 here, KPI is contained in this theory. Because I mean, so the difference between so what KPI has that M does not is bounded, so pi 0 collection and pi 1 class foundation. And pi 1 class foundation will follow from pi 1 collection. Because pi 1 collection proves pi 1 separation.
Thanks.
No, yeah.
So I guess the same thing, the same result holds in KPI, right? Instead of having M as a basis.
Yes, yeah. So the idea with this end extension result is that I'm obtaining a sigma in elementary end extension from so pi from pi n collection with the added
Yeah, M is not really playing too much of a role besides that.
well, so it's important that I'm getting kind of essentially as much of the theory of the original model I want to hold in the end extension. So Matt, I don't know if Matt's still here, but Matt has a paper that shows that with pi-n collection, one can obtain a sigma n plus 1 elementary end extension. And this will, and this will work for any model of KPI or any model of KP. But Matt's result, you can't guarantee that you can transfer theory from the base model, other than what's guaranteed by the elementarity.
I see. Thank you.
Any other questions? Okay, if not, let's thank Zach again. Thank you, Zach.
Thank you so much.
That's very good. Next week, I don't have a title for you, but we have a speaker. It's Mateusz Welik from Warsaw, and the information will be on the website soon. So.